Welcome back to Odds. In today's video, we'll be going over the forms of energy, the various forms as well as the usages of these energy, and the broader principle of conservation of energy. Okay? And how to calculate all these kinds of energy. So there's 4 forms of energy that you need to be worried about for this course, okay? There are other ones like chemical and sound, but those aren't really too easy to understand. They're more complex. So for a simpler course, you would look at these 4. Kinetic, okay, kinetic energy, gravitational, elastic, and thermal. We'll go over what each one of these means, okay? Because that's what this course aims to do, teach you what it means, right? And we will. But first, let's find out the energy units. So, if you look at any of these equations, let me just look at kinetic, okay? 1/2 mv squared. M would be in kgs, V would be in meter per second, right? When you square this, it becomes kg meter squared per second squared. Do you remember what unit this was? A joule, right? Same units as torque, but torque was represented as Newton meters. There's a difference between these two, but Newton meters is more common for torque, okay? Because torque and joule are different units. I mean, they have the same units as in simpler units, right? In base units, but they have different meanings and they can be complex and complicated sometimes. They can entangle themselves, right? That's why I write it as different units. Because energy is not the same thing as rotational motion. So it'd be a joule, right? And something you need to remember is that energy never creates or destroys. The world has a limited amount of energy, okay? And the only thing this energy can do to change is change form. It doesn't change anything else but form, okay? It transforms into a different kind of energy. Doesn't disappear and doesn't create itself. Only changes form. Okay, so now let's go over all the 4 forms of energy. But before that, there's one more thing we need to go over, okay? Conservative and non-conservative energy. So, conservative energy means it preserves the system's total energy. Okay, system's total energy. And non-conservative energy doesn't preserve it. So in the grand scheme of things, when you're looking at planetary scale, all energy is conservative, right? Because that's how Earth was made. Energy can be created or destroyed. There's only a limited amount. You can only change between forms. But non-conservative energy doesn't preserve it, as in systems. So if you look at a specific system, let's imagine a block was sliding up a ramp, right? So let's just say the system is a block in the ramp. A non-conservative force or non-conservative work would come from outside the system. So if I pushed it, and then it started sliding up by itself, the system is still the block in the ramp, but guess what? It has an additional force from me. That force is also doing work and energy, right? So that's why non-conservative work is only based on systems and where you choose to define a system. Because in this total thing, I also lost energy, right? I lost chemical energy from my food pushing it. So I did lose energy, and it was conserved. The system was conserved in the grand scheme of things. But when you look at a specific system, it could be non-conserved. Okay? And all these 3 are conservative, whereas this, thermal, you can consider both conservative or non-conservative sometimes, but it's the more non-conservative force. let's start with kinetic energy. Okay? Kinetic energy, if you remember what kinematics means motion. Any objects that moving have motion. Okay? You can imagine if a car was driving at a very high speed, it has power, right? It has energy. If it slammed into something, there would be a significant deformation. And that's energy. Okay? How do we measure this energy? Well, there's a specific equation for that. Kinetic energy is 1/2 the mass times velocity squared. Okay? So the velocity of the car, square that, and then multiply that by m, which is the mass of the car. And then by 1/2. Okay? So you're going to end up with joules. But this is the total kinetic energy of an object. And only moving objects can carry kinetic energy. Okay? Because kinetic energy depends on motion. If an object doesn't have motion, it doesn't have kinetic energy. So for example, if you're asked to find the kinetic energy of a 2 kg block, right? At 3 meters per second, it would be 1/2 times 2 kgs times 3 meters per second squared. Or it would be 9 joules. But at 6 meters per second, it would be 36 joules, right? Because it's 6 squared. So increasing velocity, right? Increasing velocity is more significant than increasing mass. Both will give you an increased kinetic energy, but only one will give you a greater change. Because here you see how it increases by a squared factor, right? So if you do by 2's, it could increase by 2's. Or 4's. If you do by 4's, it could increase by 16ths. By 8's, 64's. You get where this is going. So now let's go over the opposite of kinetic energy. When an object is not moving. Or gravitational potential energy. Okay? Potential energy in general just means it's storing that energy, okay? So if I plucked an arrow like this, you can tell that the arrow has energy, right? Because the second I release it, it goes really fast. Then it has kinetic energy. But what energy did it have before to transform into kinetic energy? It has potential energy, okay? Specifically elastic, but we'll get to that. Potential energy is energy that is stored and then is released if you do release it, okay? It's stored energy. So the potential energy of an object is equal to mgh. M is mass. G is 9.8 meters per second squared, which is acceleration due to gravity, right? And h is the height of the object. So not the distance, okay? That's something you need to be careful. Not the distance, but the height. So, for example, if you're given that an object travels d distance, then the potential energy of that object wouldn't be d. It would be d sine theta, right? Because it's the height of the object. So it depends on how high the object is. All right? So a higher object would have a equally greater gravitational potential energy. That's why it falls faster. I mean, it doesn't fall faster, but it accelerates more and has more time to fall faster, right? The higher you bring it up, the more kinetic energy it has when it's falling down, right? So similar to that. If you lifted a block, which is 5 kgs, up 2 meters, then the potential energy would be 5 kgs times the height, which is 2 meters, times gravity, acceleration due to gravity, which is 9.8 meter per second squared. So this should just be 5 times 2, 10, times 9.8, or 98 joules. Okay, only the height change counts. Now let's look at elastic energy. Elastic energy, if you remember the spring force, which we remember to be F is equal to Kx, right? Spring constant and distance from equilibrium. So what would elastic energy be? It's 1/2 Kh squared. Okay? So similar to the force, but a tad bit different. We multiply by 1/2, similar to kinetic energy, right? And then h squared, which is the distance from equilibrium. So it works the same both ways, either in a compression or a stretch, right? Like I showed you how if you compress further, it's going to have more energy to push back, right? More force, more energy. Or if you extend further, it's going to have more energy to pull back. So it works both ways. It doesn't need to apply to just springs as well, okay? So same example of the bow. This is a rubber band, right? Not a rubber band per se, but you can imagine it to be a rubber band, which has elasticity, right? Elastic potential energy. So this is also potential energy. It's not energy itself because it's not moving. I mean, not kinetic energy because it's not moving. It's storing that energy, right? So it's elastic, potential energy. So if you were to look at this diagram here, 200 Newton per meter constant, spring constant, which is squeezed 0.1 meters. And if the mass was, so the thing about elastic energy is, it doesn't look at mass, right? So your mass doesn't matter, which is a bit different from both the previous equations we saw. But you need to keep that in mind. So elastic potential energy is 1/2 times the spring constant, 200, times the distance from equilibrium. If it's squeezed 0.1 meters, that means it's squeezed 0.1 meters from equilibrium. So that squared. Okay, so it's going to give you 100 times 0.01, or just 1. All right, 1 joule. So as you can see here, it depends more on how much you compress than the spring constant, similar to the mass and velocity situation of kinetic energy. Now let's look at thermal energy. So thermal energy it could be considered both conservative and non-conservative. Okay? So for example, if you drop a block, if it has kinetic energy, why doesn't it keep moving forever? Same thing with Newton's first law, right? An object in motion stays in motion. So why wouldn't this block keep moving forever? What's that one little pestering force that moves us in the backward direction? The force of friction. This force is going to oppose that. Similarly, thermal energy is going to oppose that. So you remember, if a train is going really fast on train tracks, it's a pretty bad train, but you get the idea. You can see little glints from the metal, right? You can see little sparks like that. Or if you're cutting something with a razor, you can see sparks, right? That's why there's a lot of sparks in factories, because people are cutting stuff and moving it really close, and the friction is opposing that. Friction generates heat when it opposes something. That's why objects that move a lot have a lot of heat. Okay? Because friction is opposing that. So that's one thing friction can generate, thermal energy. And it can also generate sound. For example, if you brake a car really hard, really fast, right? You just slam the brakes on it, pushes backward immediately. You can hear that sound, right? Like the skid sound, the screeching sound. That is also friction. So that's why the energy slowly dissipates, right? Even if you started with some energy, friction is eventually going to whittle it down to nothing. So that's how it dissipates. The equation for friction is a bit tricky because we need to know another quantity before that, which I'll explain later, but right now, just come through with me, okay? What is the force of friction? Mu times n, right? Mu times normal force. Times what? The distance. Now, where is this distance coming from? You know, this is a force. What do you need to multiply this by to get a joule for energy? A meter, right? The unit for a meter, which is distance. Isn't this very similar to the torque equation? Very similar, right? And I'll explain why later, but if you just want the gist right now, the equation for work, which is also measured in the same energy, right? Which is also measured in energy, is force times distance. So whenever you have a non-conservative force, like thermal energy, or for example, if I'm moving the block up, right? That's just how much force I used to move the block and how much distance I moved it. That's my work, that's my energy. And this is also measured in joules. It'll all come together in a conservation equation that I'll show you later, but just keep that in mind. Okay? So for example, if you had a 4 kg block, right, similar to this, that slides 5 meters. So in this case, it would slide downward, however. Okay? And then mu is 0.25. This is mu k, right? Because it's kinetic friction, not static. So what is going to be the energy here of friction, thermal energy? Q is equal to same thing. So you don't need to be this fancy with Q, but you just need to know force friction times distance. Okay? Q is equal to the force of friction, which is force of friction, right? So that's mu times n. Mu 0.25 times n. So you can imagine that since they didn't give us a theta, this would just be a flat floor, right? So in the flat floor, what is n equal to? Just mg, right? So it's just going to be, what is mg here? 4 times 9.8. And then all of that times the distance, because this is force of friction, but we need to multiply that by distance, which is 5 meters. And you get 49 joules. Something I want to reiterate, which is more about the conservation of energy side of this, is that you might ask me a question, which is very common, right? If you drop a ball, then doesn't its energy change? Doesn't its energy, dissipate? That's not the case, because if you drop a ball from a height, okay? Suppose you're on a mountain. You drop it from a height above ground level. The ball is thrown. Initially, it has only potential energy, right? So you need to understand how these bars work, okay? How much it changes and how it works. Initially, it has only potential energy, which is going to be really high, right? But when it's falling in its parabolic path, let's take an instance. This instance. Imagine you use the kinematic equation and you figured out the velocity here, okay? Let's say this is halfway through the same point it started at. Then it's going to have half potential energy and half kinetic energy. But you might ask me though, where's the potential energy coming from? Isn't it just moving? But remember, even if it's moving, it still has a height, right? But it has a lower height, so it'll have a lower energy. And what is it going to trade that energy for? kinetic energy. So these two always complement each other in many ways. And at the very end, like right before it hits the ground, okay? Because once it hits the ground, it generates sound, which is going to bounce off the floor, right? It generates sound here. It's also going to generate heat on the floor. So that's the energy that's going to be dissipating. But what is the energy right before it hits the floor? It's going to be all kinetic, right? We can assume the height is basically 0. So then it would be all kinetic. So this is how the bars change here, okay? Potential, and then potential kinetic, and then kinetic energy. And if it was to bounce up, then your bars would look like this. So friction would take some of it, right? Force of friction times resistance, or sound and heat, you can imagine, right? That would take some of the energy. And what else would beat the bars? It would also, once it bounces up, it gets a potential energy, right? And then over here, its kinetic energy is also going to be there. So something you want to remember is that at any point where the ball is at its height, okay, the vertex of its parabolic motion, do you remember from kinematics what the velocity over here would be? Velocity would be 0, right? So if the velocity is 0, all the kinetic energy is gone. And what's the only thing going to be left? Potential energy. And then it falls again, and then it changes. I mean, in this specific scenario, some of the energy was eaten away by the friction, right? But imagine that it wasn't, then in this case, it would just be only potential energy. So let's try some problems, okay? These are the most basic ones, obviously. We'll be going over the harder ones, as well as conservation of momentum and energy equations. Those are the more complex parts of this unit, as well as the problems I'll be pushing out on autolearning.com as a PDF. But right now, let's just make sure we know what we're doing. The kinetic energy of a cart, 4 kg cart that moves at 5 meters per second. That would just be 1/2 times 4 kg times 5 meters per second squared, right? So this should just be 2 kgs times 25 meters squared per second squared, or 50 joules. Let me erase this. So 50 joules. A 2 kg book rests on a shelf 1.8 meters high. Okay, so the shelf is over here. And this is the book. Shelf. And the length of the shelf is 1.8 meters. In this case, it's height. Okay, length as in height, not as in the distance. And the mass of the book is 2 kgs. So what is its gravitational potential energy? That's equal to mgh, right? So m here, 2 kgs. G here, 9.81 meter per second squared. I'll just use 9.8. And that times 1.8 meters of height. So if you have your calculator out, which you should, right, you'll be getting 2 times 1.8 times 9.8, which is 35.28 joules. Okay? And also one more question that I often get: if gravitational potential energy is mgh, then that increases if the mass increases, right? Which makes sense. A heavier object is going to hit the ground harder, right? You would rather be hit by a ball dropped from the same height than an iron block. Makes a lot of sense. But then, didn't we say that there's no correlation between mass and acceleration in unit 2, right? When we're going over Newton's laws. That's because mass and acceleration here, that's the force of gravity, okay? That acts similarly for everything. But the energy is a bit different. Force of gravity is how much force the earth exerts to pull you downwards towards it. Energy is how much energy the object has, right? How hard can it hit? What's its power? So that's what energy is. And if you have a higher mass, the object can hit harder. Okay, so for problem 3, a K, which is a spring constant, of 300 Newton per meter spring is stretched to 0.2 meter. Find the stored elastic energy. So, what is the energy of a spring? Elastic energy of a spring? 1/2 kx squared. 1/2 times 300 times 0.2 squared, right? Or in other words, 150 times 0.04, which is just 6 newtons. Okay? And as always, okay, if I gave you 20 centimeters instead of meters, that would have tripped you up, right? You could have plugged in 20, but the units of joules are not centimeters, they're meters. So you have to always convert it to the SI units. That's why units are so important. That's why I spent a lot of time in them on unit 1. Okay? And I wrote 6 newtons here, but it's actually 6 joules. Slight error on my part. A 6 kg crate slides 3 meters across the floor. Okay, 3 meters across the floor. Now, mu k is 0.3. I need to find the thermal energy produced. So we can write it as Q, which is a bit more formal, but it's fine, right? We can just write it as force of friction times distance, or work done by friction. It's just going to be the force of friction times distance, right? And the force of friction here would be mu k times the normal force. Mu k is 0.3. The normal force is directly going to match up to gravity, right? Because it's just a flat floor. mg here is 6 times 9.8. And all of that times 3 meters. So this is kgs, or no, this one doesn't have units. This is kgs. This is meter per second squared. So the units match up. So if you multiply this out, you should get 52.92 joules. Okay? And that's your answer. Alright, so feel free to check out my other videos on this, which I'll be posting soon, as well as the PDFs regarding this, because these are only the beginning of energy. Stay tuned and give me a like and subscribe so I can reach more people and help more like you.